So let's go ahead and just look at a couple of examples of probability using a given sample space. So on this one, we want to find the probability. This is the two die. In other words, if you get a die with 6 sides and another die with 6 sides and you roll them together, then you can have 36 outcomes because of the counting principle. 6 times 6 gives you 36. And these are the 36 outcomes. The 36 outcomes, well, you could have a 1 and a 1 on your die. You could have a 2 and a 1 or a 1 and a 2. And these things kind of follow a pattern. See, this is the 2 row. This was just, there's just one row. There's more possibilities for 3. There's 3 of them. 4 possibilities. I'm sorry, that was the 5 row. I'm sorry, the 4 row. They all add up to 4, and this one's 5. And each time we go up, we add another one. This is the 6 row. Everything adds up to 6. 6, 6, 6, 6, 6. And then you got a 7 row. And hopefully you can see the pattern. Like this is the 12. This is the 11. Everything on that is 10. This is 9. And then this is 8. Okay, so there's a row in there that represents each one of the sums. All right, so probability of getting a 9. Well, let's put a little check mark wherever there's a 9. Well, here's 6 and 3 is 9. 5 and 4 is 9. 4 and 5 is 9. And 3 and 6 is 9. So all of those on that row are equal to 9. So that's the probability of 4 of some equal to 9 is equal to 4 over a total of 36. And simplifying that, both are divisible by 4. So this is 1/9 would be that probability. Kind of a neat coincidence that it comes out to that sum being in your denominator for the probability, but what's your okay. So here's another one. The sum is an even number. So even numbers. A sum that is an even number. Well, we can start marking them, and that's usually the best way. But what do you notice here? So this is 1 and 2. So that's 1 and 1 is 2. So that's even. So 2 and 1 is 3. 1 and 2 is 3. So not this one, but this one is even. See, because those are all 4s. 5, 5, 5, 5. So that's not even. But here's some more evens. The 6 row. Here's 7 in there, but let's go on to 8. Since 8 is even. 9, of course, is not, but 10 is. 11 is not. So we got a lot of them here. And what is that? Well, probability. How many do you think that is?
I counted 17, but I'm not sure.
Isn't it like half of them?
Half.
Look, 1, 2, 3. So half of 6. 1, 2, 3. Half of 6 again. 1, 2, 3. Half of 6 again. 1, 2, 3. 1, 2, 3. 1, 2, 3. So it's not 17. It's
18.
18. And 18 over 36 is equal to 1/2. So the probability of it being a sum and even number is 1/2 because half of them are even. The other half are odd. And the next one was sum greater than 8. So a sum greater than 8. So let's go back up there and look. And we're looking for the ones that the sum is greater than 8. So this one is greater than 8 because 6 and 6 is 12. 5 and 6 is 11, as well as 6 and 5 are 11. Here's 10, 10, 10. What did it say? Did it say greater than 9? Oh, greater than 8. Okay, so I can keep going. Because 9 is greater than 8. But it does not say greater than or equal to 8, so we're not going to include the x, the 8 row. So it stops. And all of these over here are going to be less than. I'm not even going to mark them all because we don't need them. We only need these that are in green, which is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the probability of sum is greater than 8. So on the denominator, it's 36. And I already forgot how many it was. How many was there? Oh, it's such green check marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 over 36. And that could be simplified to 5/18 because they're both divisible by 2. All right. All right. So let's do one more. This is one of my favorite ones to do with the children because it really works like a coin flip in that there's only 2 choices for each child, boy or girl. All right. So find the probability of having a family with at least 2 girls. 2 girls. All right. So we already got the sample space. So how many of these have at least 2 girls? This one, the first one, boy, 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 doesn't have any girls. Boy, boy, girl, that's only got 1. Again, boy, girl, boy has only got one. This one has one. So I'm going to check that one. This one's got two boys, so not that one. And all the rest of them have at least one girl. 1, 2, 3, 4. So this is going to be 4 over 8, which is equal to 1/2. All right, so what else we got? We got find the probability of having all children of the same gender. All right, all same gender. That's these right here. There's only 2 of those. All right. So then the probability of all the same gender. Well, I already got it right there. It's right there. So it's 2 over 8, because there was 2 circles that were fit that criteria, all boy, 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 and girl, girl, girl. So 2/8 is equal to 1/4. We always simplify the fractions. Sometimes they will ask you to write it as a decimal, and make sure you can do that, because I went through that thing, and half the time it's asking for the simplified fraction and sometimes the decimal. So if we wanted to do the decimal, then 1 divided by 2 would be the same thing as 4 divided by 8. So then this would be 0.5. Oh, I'm sorry. It was this one we were doing. Two eight. So that would be 0.25. And remember, all you do to find that is just take the numerator and divide it by the denominator. It doesn't even have to be simplified in order to do it. Because if you do 2 divided by 8, you get 5. If you take 1 and divide it by 4, you get 0.25. All right. Probability of having exactly 2 girls. Exactly 2 girls. All right. So we look for the ones that have exactly 2 girls. Exactly 2 girls. We don't want ones that's got more than 2 girls. We don't want any that's got a less than 2 girls. We want ones that have exactly 2 girls. And that would be this one and this one. Because the first one, it doesn't have any girls. The second one has 1 girl. Third one, 1 girl. The fourth one, boy, girl, girl. That's got exactly 2. Girl, boy, boy. It's only got 1 girl, but this one has a second one, and this one has a second one. This one is not exactly All right. It's at least two. So we're not looking at this one. We're looking at exactly two girls down there. So there's three of them. So 3/8. And again, for your fraction, if they ask you for the decimal, you would just take it. And that's what you'd put in. Watch out what they ask you to round to, because sometimes it says 2, sometimes it says 3. All right. So cards are another kind of interesting sample space. It's got a nice pattern to it. You've got 52 cards in a standard deck of cards. And there's 4 suits. The one at the top, this is a club, and exactly 1/4 of the deck are clubs. In other words, there's 13 clubs there. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, and King. The Jack is sort of the 11, the Queen 12, and the King 13. And of course, the Ace is 1. And so the same thing with the hearts. There's 13. 13 spades, 13 diamonds. So 4 suits, each the same size. So here's what we're going to use for this. If I can get everything on one page. There we go. All right. So the first thing we want to find is the probability of an ace. So there are 1, 2, 3, 4 aces. So imagine what you're doing with this deck. You're letting someone pick, or you're handing them one card out of a shuffled deck, a random deck. So the probability of an ace is equal to 4, and the total is 52. Now, a face card. A face card. Well, that's all of these over here, the Jack. And how many are those? There's 12, right? So there's 12 over 52. And then we can simplify that.
So, Mr. Cruz, you don't simplify the 4/52?
Oh, sorry. Thanks for noticing that. Yeah. So that's and watch what's going to happen here. It's 1/13. And you can see that pattern here, because for each one of these rows, each one of these suits, there's exactly one ace, 1 out of 13. So here, let's see, it would be, we might do it in 2 hops here. If we divide both of them by 2, we get 6/26. It's still even. So 3/13. And again, you'll notice that same pattern, that in each one of the suits, there's exactly 3 of the 13 that are face cards. All right, a club. Well, here, the clubs are a whole suit. All right. And how many of them are there? 13 of them. Probability of a club is equal to 13 over 52, which is equal to 1/4. 1/4 of the deck is clubs. All right. A 4 or a heart. All right, we got to watch this now. Here's the 4s. Here's the hearts. There's 13 hearts and there's 4 clubs, but we got a little problem here. And this is why we had that little rule for the number of elements in the union of two sets, that it's the sum of the number in A and the number in B minus any that are the same. So the reason why is we don't want to count things twice. And that's what would happen here if we don't notice this. So we got 13. The 4 clubs is our 14th. We're going to skip that one since we already counted it. 15 and then 16. So be very careful. So there's 16 over 52. So both divisible by 4. So 4/13. Because 16 is divisible by 4 times, and 52 is divisible. So 4/13. All right, this last one's kind of, we got to pay a little bit of attention to it. It says a 6 or an 8 of spades. In other words, 6 of spades, 8 of spades. There's no comma. So 1, 2. So there's 2 out of the total of 52. And both of those are divisible by 2. So 1/26. All right, so that's the basic probability. And in this little part, I've just been concentrating on, let's looking at some sample spaces and bring them over. But in reality, the way that we deal with probability is not always going to be so cut and dry. So the reason why we went over those counting methods is because we can sometimes save ourselves a lot of work by using permutations, combinations, and the counting principle. Okay. In other words, it's not important to know exactly what those 6 that are at least 2 when we were talking about the winning the pool games, we don't need to know that they're what the six are, what the order are, like what was it, Mark, Raul, Rule, Mark, that kind of thing. We don't really need to know what they are. We just need to know how many there are. Okay, so then we can use our counting methods, our multiplication property principle, and we can use permutations and combinations and probability. Remember, order means that we use permutations. No order means we use combinations. All right, let's look at a few of these things. All right, we have a club that consists of 5 men and 7 women. So we got 12 club members. We got 5 men, 7 women. What's going to happen here is we're going to pick 3 of these people and send them to a conference. This often happens with teachers. They try to get us to go to conferences and stuff. And so we want to pick 3 people out of these 12 to go to the conference. Now, what we want to find out is not how many we're going to need that value, but we want to find the probability that the selected group consists of 3 men. All right. Probability of 3 men. All right. So the way that we do it is, and you can kind of see this, I don't have all the details, but we're going to pick the number of ways of selecting 3 men. The numerator is always for the specific event, in this case, the 3 men that we want. And the denominator is all of them. Okay? So what I'm going to do here, I'm going to make a fraction. I probably shouldn't be using that color. All right. So what we're going to have down here and we've got 12 members that we're going to be picking from. And out of those 12, we're picking 3. So if we just look at that bottom number, well, this is the thing that doesn't have that. Oh, I got one somewhere else. So we got 12 and we're picking 3. The same thing you would get with your calculator. So there should be 220 then here at the bottom. So let's go back over there. So that denominator that we just calculated is going to be right there. And then up here, we're going to have 2 things. We're going to have, we put a couple of big C's. We're going to multiply the number of ways to pick the women and the number of ways to pick the men. All right. Now, so this would be men. And then this is women. So therefore, for the men, there's 5 of them. And we want to pick 3 of those. All right. And then we don't want any women. So we're picking 0 out of 7. We could almost leave that out because that's just going to be 1. All right. But now let's go back over to that combinations calculator and do the 5, 3. So what was it? It was 10. And as I said, you're multiplying here times a 1, and I'll show you in a second that it is 1. If you're picking 0 out of 7, there's only one way to do it. Doesn't matter what you pick. If you're picking 0, there's one way to do it. Okay. So this is going to be 10 over 220. And we can knock off one of the zeros, and the probability would be 1 over 22. So one of the reasons that I like this problem is just because it's kind of got a practical element to it. Let's say that there's this scenario exists, and these guys are wondering what the probability is of them being able to get 3 guys going on this so they can have guy kind of fun, all right? Well, if you come out with a probability of 1 over 22, and we do that with a decimal to kind of give it a little bit better perspective, 1 divided by 22 is 0.045. In other words, that's less than 5%. So that's a kind of what we would call in statistics a rare event. So we're not looking forward to that happening. 4.5% chance of something happening. It could happen, but don't sit around and wait for it. All right, y'all still hanging in there?
I'm here.
Y'all okay? All right.
I mean, for the most part, I mean.
What is that video you got there, Chantel? Is that a ceiling fan or is that something else?
It looks frozen.
All right. So let's look at the idea of a lock, and this is why the things are kind of sometimes hard to understand, because the word that we use for permutation in mathematics generally doesn't get used in the regular street language, like people would just say combinations. Okay. So what we need to do is we need to find out here in this situation, it's called a permit. It would in actuality be a permutation lock because the numbers in the combination have to be in order. So a thief has 10 tries at opening the above lock. What is the probability he can open it in those 10 tries? Well, all right. Well, we're kind of told, how many tries he's got. So what are we going to have down here? Well, we're going to have our permutations. We need 3 numbers picked out of how many? How many numbers are there on there? It's tempting to say 39, but it's 40 because the 0 counts as 1. So 40 Picking 3. And then if we simplify that, and we can just knock off the zeros. So depending on whether order is important, you use combinations. If they're not important, permutations if there are. The lottery is one of those that is really interesting because it uses combinations if you didn't know about it. But the Powerball is a combination of the state lottery, the 1 through 5, the pick 5, and then the Powerball is an additional one that gets added to it. Well, this is how it kind of works. All right. If our numbers, if we have available to pick is 1 through 69, and we're picking 5, so that's what that would be here. Then for the state lottery, in other words, for the Louisiana part, the pick 5, it's 11,238,513 ways to do it. That many numbers to pick. Now, the Powerball gets multiplied by that number right there, and it gives us 292,201,338. So the probability of one ticket win would be 1 over, and then it goes down here is the 292. And however many additional tickets you buy, you would just put them up there. In other words, if you bought 10 tickets, then it would be 1-0 up there. And then you can simplify it. Well, that's simplified as far as a fraction is concerned, but let's say we want to just know what that is decimal wise. So see that problem right there? Whew. I bet you most people can't figure out what that's going to be because scientific notation. And this is one of the things that drives people mad about calculators. Calculators are not the smartest things that you can come up with. The problem being with a calculator, it's only got limited room for it to lay everything out. So what that right there means is it means 3.422. I'm not going to go all the way down here. And then it's going to have a bunch of zeros. So watch what I'm talking about. So what's going to happen is it said 9 zeros. So watch this. All right. Now, we got to hop 9 times. It said -9. So we're going 1, 2, 3, 4, 5, 6, 7, 8, and 9. So see, that would be what that represents. So that's the decimal value for that fraction. Very, very small. Because you got, let's see, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 millions, and so forth. So a lot of them out there, a lot of zeros.
Mr.
All
Cruz,
right.
the lock, the permutation lock.
Hold on a second, Tori. For some reason, your voice is low.
Hold on. Can you hear me?
Yeah, I hear you better now.
Okay. So that permutation lock, whenever I do the 40 permutation 3, I'm coming up with like 52,000
That's probably right. Let me go back and check it because when I was doing it,
or 50. Yeah.
oh, that's combinations. Okay. Sorry. I
Well, at
said
the bottom of the problem, it says it's a
this
combination
one.
order. And that's why I was confused too. Do I use combinations or
No,
permutations?
you do. That's it said permutations, and then I used
Okay.
the combinations because that one is just combinations. So here we go. I thought something was funny about that, but I didn't want to spend too much time talking about it. But yeah, let's go back over and fix it. Yeah, exactly. I'm thank you for doing that. So let's go ahead and fix this. There we go. Oh, and it's a 10, right? It's still going to do the same thing.
Tries. Yeah.
So it ends up being one over. And then we just knock off the 0. So 5,928. Yeah, well, sorry about that, about not noticing that. I don't know why. I got another one that I generally use. And so that's why I usually stick on the calculator, but that calculator is kind of a pain in the neck to get to in Alex. And I can do it here, but I wanted y'all to be able to see it. All right, well, that's good. We got that cleared up. All right, we're going to come back to odds. And we're going to come back to expected value. Because the way that that Newton works it, they go and they jump on the or in the and probability first. All right. So the two big rules for probability, or the two biggest rules we have so far, is or probability. Or probability. So let me put this up here. Or means add. Okay. That's the same thing as the union. When you find the union, you add up all of the ones in your union. You add up what's in the first set and then the second set. And if there are any that are common to both, you subtract those out. Okay. All right. So or means add. Or means add. All right. And that formula that we talked about within chapter 2 with the set theory, that fits here. We use the exact same thing, except that it looked sort of like this. Actually, it was U. We used the U. should be equal. So see, that's that same thing. It's just now we're using it with probability. Well, it still holds. So it's not new. We're just kind of getting it again now in a different context. Now remember, there's two different types of probability when we're talking about, remember, the unions and ors, right? We have mutually exclusive, which was like this one here. Mutually exclusive. Notice that there's no touching. They do not overlap. They have no common elements. Over here, they do have common elements. So there are some that be common to both. In this event here, if they're like this, then this part right here is going to be 0 because there is no overlap. Okay? So this is really the formula that we need. Is just this one that I've already talked about right there. But if they are mutually exclusive, then this is going to be 0. Just remember that. There's only that one formula. And if that is 0, if they're mutually exclusive, then it ends up collapsing into just probability of A and probability of B if they're mutually exclusive. Okay. So here we're going to find the probability of picking a club or a red card. So we got the or means add, and that's that formula. So we need the probability of a club plus the probability of red minus the probability of club and red. Let me see if I can get a deck of cards here. So that we can view it while we're, I guess it doesn't really matter which one. All right. So we need a probability of a club plus the probability of a red. So how many clubs are there? 1, 2, 3, 4, 5, 6, 7, 8, 13, right? So the probability of a club is 13 over 52. The probability of red, well, red is half the deck. In other words, 26 cards are red. Now, are there any that are red and a club? Any cards that are red and a club?
No, clubs are black.
There's what we call mutually exclusive. Okay, good. So this right here is 0. You don't have to put it if you don't want to, but I'm just trying to show you that formula, that this one formula here works for both mutually exclusive and non-mutually exclusive. And it's the same formula from chapter 2. So this is going to be 39 over 52, which is 3/4 of the deck is club or red. And you can see that there. So club is 13 of them, and 26 of them are red. The only one that's not included is the aces. All right, again, this is OR probability. Find the probability of rolling a 6 on a die or flipping a coin to get ahead. So again, to get the whole thing laid out here, die or pulling head. All right, and so that's going to be the probability of the 6. I'm going to try to shorten things down a bit here to make it where it doesn't take up so much room. Now we're dealing with what we call independent events here, but there's no possibility of this happen. This is what we call mutually exclusive because there are no 6 and heads on one coin or one die. It's just a matter of those are independent events and therefore they're mutually exclusive. So it's simply this. So die equal to 1/6 is to 6 is equal to 1/6. Probability of a head is 1/2. I'm sorry. Yeah, 1/2. And so to add those up, well, we got to have a common denominator. So what I'm going to do, I'm going to make the second one into 3/6, since that's 1/2 with the denominator of 6. So 4/6 is equal to 2/3. So OR probability is just adding. If they're mutually exclusive, then there's nothing to subtract. All right.
So we didn't add the probability of 6 and head. We didn't add those together.
Yeah, I did. Look. 1/6 plus 3/6 is equal to 4/6.
Okay.
Yeah, I added them. Just you have to have a common denominator in this case. All right. Here's one more we can try that's mutually exclusive. No, that's what I'd say. That's enough mutually exclusive. Let's do this one with here. What is the probability of selecting a red card from a deck of 52 or picking an ace? All right. Okay, so this is going to be the probability of the red plus the probability of the ace minus the probability of red and ace. Okay, so I'm just going to write down here the probability of each one of those. There's half of the red deck. I mean, the card is red, so this is 26 over 52. I'm not simplifying them when I'm adding them, so that's, we want them to have the same denominator if possible. So don't simplify them yet. When you're adding, you simplify at the end. All right, and then there's because there's these right here are the 26 that are red. The aces are these 4. So there's 4 of those over 52. So I got the same denominator, so it didn't add as easy here. 26 plus 4 is 30. Whoops, whoop, whoop, whoop. I forgot to do something. Now we need how many are red and ace? Red and ace. Well, there's only 2 of those, right? Two of the aces are red. These are not mutually exclusive because they can be both red and ace. So this is going to be 26 and 4 is 30 minus 2 would be 28 over 52. So then let's see, that's I think that's 7 over 13. Because 28 divided by 4 is 7 and 52 divided by 4 is 13. So see that? We had to subtract out. Just like in chapter 2, if we have sets that are not mutually exclusive, because if they're not mutually exclusive, you don't count them twice. All right. Let me see if there's anything else I can do here to end. All right, let's do this last one. My brain wants to get out of here early, but let's try one more that involves not mutually exclusive. All right. In one class, there are 15 freshmen and 10 sophomores, so that's 25 students. Total students. 6 of the freshmen are education majors, and 4 of the sophomores are education majors. Now we're anticipating a random event here. We're just going to pull out, find the probability that the student is a sophomore or education major. So again, I'm just going to put it in the formula. So sophomore education major equal to probability of sophomore plus the probability of EDU minus the probability of soph and EDU. All right. So we need to find each one of those. So how many sophomores are there? 10 of the 25 are sophomores. So education majors, there's 6 and 4. Okay, so that's what's going to go here. They both happen to be 10. And then how many are both sophomore and education? Well, there's 4 of them. 4 sophomores are education majors. So then this 20 minus 4 is 16 over 25. If we simplify it there. The best rule of practice is when you're doing these, don't simplify these until you get to the very end when you're doing the adding. Because if you simplify it, then you're going to have to write it. You're going to have to possibly create a common denominator. All right. That's where I'm going to stop at. So if you got any questions, stick around.
No thanks. Have a good evening. Thank you.
Okay, you too. Bye-bye.
Bye.
Thank you. Bye.
Justice, you okay? I think there are some. Remind me tomorrow to see if there's something I need to do, because the last week I did it and I was able to give a little extra time. So I can't remember if I did all that. So remind me tomorrow. The homework will be a little bit slower. The homework will be a little bit slower this time. It's just kind of, there's not as much of it as there has been. So just try to get a start on it. Well, actually, I saw you'd already gone in and done about 2 or 3 of them. You had them maxed out 100 each. So you should be all right. Isn't that what you did? I'm pretty sure you had like a bunch of them done. Yeah, you got the probability. Yeah. What I'll do is after I go down and finish the and I'll come back and then do the odds and expectation together. So you should be all right. But talk to me tomorrow if you need anything, okay? Like extension or what. I think I will be all right this time. See ya.